it's important to have two things in your mind. So one thing is something called duality between compact abelian groups and discrete abelian groups. So for example, the duality between circle and integers, so on, Ergodic Theory. And this means that to construct examples of compact abelian groups, it's the same as constructing examples of discrete abelian groups. And if you want them to be metric, then you just need to ensure they're countable. And if you want these two to be connected, it's enough for these to be torsion-free, and so on. So somehow everything can be done in either of two languages. And that means it's in order to understand what I want to talk about, you need to have a big list of compact groups, or equivalently a big list of discrete countable groups in your mind. And there is one particular group that is very important in this subject. That's Q, which corresponds under this duality to something. And Q has a distinguished subgroup Z, corresponds to a circle, and in between there are many distinct subgroups. So, and I want you to think of them in a certain way. So, down here is things like Z1 half, Z1 third, and so on. These are all different in the sense they're mutually non-isomorphic. Up here are things that in ring theory you would call localizations. Things where you invert all but a single prime. In between there are many things, and the interesting things, or to me interesting things I'll talk about at the end, all happen in the middle here. And then it's also important to know that there are many other subgroups of Q, other than these guys. There are things like the subgroup of rationals with square-free denominator. That's an additive subgroup, which is none of these things. But it's a different group because it's not cyclic. Okay, so there's lots of subgroups. And by duality, there are lots of compact groups over here that are mutually non-isomorphic.
So X, Adelsmore cube.
Yeah, Adelsmore cube. And then you can describe all these guys in that language, right? You just modify the construction. These other things are just different. They're just other projective limits of circles. So the question I want to ask is, can you describe compact group automorphisms as a whole, modulo dynamical equivalences? So the setup is this: a continuous group automorphism on a compact metric space, compact abelian group.
So in that picture, actually, you just remark that X is Adels.
Oh, so you can describe, if you know this language, then and you can use the same construction by modifying, emitting certain primes for all of these guys, but you can't for the other subgroups. But this gives a very nice geometrical way of thinking. So, the example I want to study are continuous group automorphisms of compact metric groups. And of course, these things preserve a distinguished measure. They have by hypothesis, they have a metric, so they are topological dynamical systems. And these are extremely special, and in the context of this meeting particularly, they are much more rigid than the algebraic examples we've heard about. So there are no flows. There is nothing, there is no topology in which it's reasonable to think of an automorphism being close to another automorphism. Right? The natural topology of the automorphism group is always discrete. And that means that you cannot take an example and perturb it. And You can't use machinery of flowing for a period of time, flowing for a short period of time, or anything like that. The dynamics is, despite the title, is much more homogeneous than homogeneous dynamics. So in homogeneous dynamics, you typically have cusps where things are distorted very much. In these kind of systems, if you are an ant living on G, then the map will do something to you. Something like this. And it will transport you somewhere. This geometrical picture, if I ignore the displacement, is identical everywhere. Isometrically identical everywhere. So there's no escaping to infinity or anything like that. And of course, just ignore this. You can ask the same kind of question about group actions by automorphisms. I want to concentrate on a single automorphism. I also want to avoid examples like the identity map. So in this subject, that is just assuming that the map T is ergodic, which means there's no invariant functions. And then the problem I want to address is this one. I think of all such examples simultaneously, all compact metric abelian groups, all automorphisms. This is a collection of dynamical systems. I will have some notion of equivalence, and I want to describe the quotient space. So this is somehow attempting to classify something. And the starting point would always be a commutative diagram, some kind of continuum. So I have two examples, G1 and G2, two compact groups, two automorphisms, T1 and T2, and some map intertwining them. And this map might be an actual isomorphism of groups, continuous isomorphism of groups. So this is somehow, say, identical inside this category. Or it might be simply a homeomorphism, topological conjugacy between them, or a measurable isomorphism, which is just a measurable match from G1 to G2 that takes Haar measure to Haar measure, doesn't need to be defined everywhere, need not respect any other structure, but commutes with intertwines the maps T1 and T2. These are obviously related. So any algebraic isomorphism is a topological conjugacy just because you assume it's a continuous isomorphism. Not so obviously, topological conjugacy implies measurable isomorphism. This is true, but somehow doesn't seem to be an elementary fact, unless someone can tell me otherwise. You need to know something to know this is true, because you need to know something about maximal measures or other things, but
Haar measures.
yeah. What?
Invariance of Haar measure.
That a topological conjugacy preserves Haar measure?
No.
Why should it do that?
Okay.
Maximum. Yeah, if you know unique maximal, if you know that Haar measure is uniquely maximal, then there's some argument. But you need to know something. You need to do something. So I just want to talk very briefly about these three things in turn, and then explain why I think this is all such a mess. So algebraic isomorphism is not to do with dynamics at all. It's simply, if I hand you a single compact group, or two groups that are isomorphic, so I might as well think of them as a single compact group, and two automorphisms, and you tell me whether they're conjugate in the automorphism group. So this is somehow a familiar problem, and just for those who don't know this stuff, I should mention that immediately becomes a little complicated, even in familiar situations. So in the two torus, for example, conjugacy of elements of the two torus in this algebraic sense requires an additional invariant. Right? If two matrices are, this is a nice example, if two matrices share the same characteristic polynomial, it doesn't follow that they're conjugate over the integers. You need some additional information. This is one of many standard examples. It's a nice exercise. If you write down a matrix that conjugates these two, then you can just manipulate the equations and convince yourself that the matrix will have some determinant that isn't 1 or minus 1. It's even or something like that. There is some obstruction. And this obstruction is very interesting and sort of does have a dynamical meaning. The third invariant in number theory is somehow connected with the ideal class group of the splitting field, the relevant splitting field. This is some very classical observation and makes sense for a torus of any dimension. And more recently, you can describe in dynamical terms this other invariant you need to distinguish these things. An invariant that will tell you those two Toral automorphisms are different algebraically, and you can describe it in various ways. So that's just an example of somehow what happens in the algebraic conjugacy problem, but certainly it's completely an algebra question. Topological conjugacy, on the face of it, is different because you're not required to preserve the group structure. And here is an important example, different to any of these. If I take two finite groups and use them as alphabets to construct full shifts, then I have two very simple examples of compact group automorphisms in which nothing is preserved by topological conjugacy, or almost nothing. So if G and H have the same cardinality, then any bijection between G and H extends to a homeomorphism between the shift spaces, shift commuting homeomorphism. And so the cardinalities are visible, right? Because the cardinality of the alphabet is the number of fixed points, which is an invariant. But nothing else is visible. So for these guys, all the algebraic structure is lost in the topological conjugacy, and that means that somehow on totally disconnected groups, topological conjugacy is just not telling you. If the groups are connected, it's reasonable to start to think, if you try and construct a topological conjugacy between two such systems and make some choice of what it will take at this point to over here, then you can imagine moving away from this point in this connected group and being forced to do something in this connected group. And that's what happens. Topological structure is very rigid here. And I just want to go through a very elementary example slowly. So imagine I had two tall automorphisms that were topologically conjugate. Then, of course, their dimensions must be equal, because dimension is visible to topological conjugacy. And so that's your first observation. D and E must be the same. But I can also linearize this guy. So somehow, in all this business, being able to linearize things is a very important difference between these kind of dynamical systems and things like G1 gamma dynamics. Here you can completely linearize very successfully and very easily. And in fact, this opaque, forgive me if you don't know what it means, but clear if you do know what it means, this is a linearization. Because it means that locally this guy, whatever it is, looks like this. Because this is a discrete subgroup. And a diagram like this, you have many ways to linearize. You could lift covering spaces, or you could apply fundamental group functor or anything. There are many ways to linearize this diagram. This is one way. I can apply I1, and this changes this diagram into an upgrade, because I1 of phi is some automorphism of ZB. So up to maybe writing down transposes somewhere, A and B must become conjugate in GLDZ. So I've reduced back to an upgrade isomorphism. And this is roughly the picture that on totally disconnected groups, topological conjugacy is just very difficult to interpret. On connected groups, it's essentially algebraic. And in fact, you can do the same on all these strange creatures here. There are more sophisticated functors you can use to linearize. And back again, this is all a bit deceptive. I start with this topological picture, I linearize, I get an algebraic picture, but somehow, in hindsight, is the wrong point of view. So a very beautiful paper of Adler and Palais from 1965 says that if I have a topological conjugacy between two ergodic automorphisms, there is a different argument that says that the conjugacy itself is linear, always affine. But that there are no exotic topological conjugacies between two automorphisms. They're just the ones you can write down with their names. And they are rigid. There's this topological rigidity. And this also, on these other things analogous to torus called solenoids, the same thing happens. That the topological conjugacies themselves are affine maps. So somehow this is pretty much all one can say. If I ask the same questions for group actions, I get different phenomena. I'll try and say a little bit about, but this is all one can say. So, in pursuit of an understanding of this quotient space, modulo topological conjugacy, you could write down invariants. This is the simplest invariant to write down. One of the invariants to write down. That is just a generating function, that a formal generating function that counts periodic points for the automorphism. This is the dynamical zeta function. And of course, topological conjugacy would preserve this function. And this phenomena that you learn little on totally disconnected groups is visible here. So the shift automorphism on a finite alphabet, the zeta function remembers the cardinality but remembers nothing else. And on connected groups, you would expect this topological rigidity to produce an argument that goes roughly with some constraints. If I tell you the zeta function, I've told you a great deal of information about the group and so on, but that's not quite true. This is a very nice example, I think. There are uncountably many different, topologically different automorphisms of one-dimensional solenoids with the same zeta function. So this means that somehow, even on connected groups, periodic point counting alone doesn't tell you very much. It tells you something. And the reason is this phenomenon that Q has many subgroups. And in fact, this example doesn't come from this part of the picture at all, it comes from this other part. Q has many strange subgroups to do with controlling the shape of the denominator of the elements of that subgroup. Okay. So now, the most interesting one probably is measurable isomorphism, the most natural in ergodic theory. And of course, this is very difficult to understand because measurable isomorphisms can do a lot of damage to the appearance of a compact group. Okay, so in particular, all infinite compact abelian metric groups are measurably indistinguishable from each other as measure spaces. They are all the same. So the impact of having to intertwine given automorphisms is much more significant. Okay? This is really dynamics, not algebra. And there are two relevant theorems, both actually very substantial things. So one of them is that all these examples are measurably isomorphic to Bernoulli shifts. That means there is a way of chopping the group up into countably many measurable sets. And if I use that partition and refine it under the action of the automorphism, I will end up with a description of this system as an IID process. So essentially, measurably, it looks like a full shift on some countable algebra. So this is somehow a structural statement about group automorphisms. Here means T is measurably indistinguishable from the shift map countable alphabet, which I might as well take to be the natural numbers, serving some IID product measure given by some vector, some probability vector, A1 up to A2 and so on. And then a very profound fact is that Bernoulli shifts aren't measurably classical. This is Ornstein theory. But there is a numerical invariant that I can attach to this probability vector, A1, A2, and so on, that tells me when they are isomorphic. So this numerical invariant is the measure theoretic entropy, and Ornstein's theorem is that two Bernoulli shifts of the same entropy are measurably isomorphic. So I kind of have a complete description of the situation, of the situation I was interested in using these two very deep theorems. But it doesn't really tell you anything, right? Or it doesn't tell you much. It tells you that if tilde is measurable isomorphism, then I can describe G mod tilde using real numbers, using the entropy parameter, but it doesn't tell me what entropies appear. So in order to say more, you need to know how to compute the entropy of these things, and this is where the fact that group automorphisms are extremely homogeneous means that you can choose to calculate things globally or locally just as you like. So you can compute the entropy of a group automorphism in a neighborhood of the identity just by measuring the decay of Bowen balls. So in effect, you would take an ant located at the identity, move it under the transformation, or perhaps the inverse transformation, intersect it with itself, compute the volume of this intersection, keep iterating and intersecting. You would expect exponential decay governed by the dilation factors in different directions. So I expect this intersection of an epsilon ball to be exponentially decaying. I measure the exponential decay rate, then it's a theorem that this quantity is the entropy in the same sense that you need for the Bernoulli theory. It's very back to Bowen. So, this is, I guess, due to Bowen. This coincides with the entropy of the Bernoulli shift that T is isomorphic to. So how does this formula look? So Kuzminski computed this in general, and just to understand it, just to write down this observation more precisely. If I have a toral automorphism, this is always the simplest example, with some eigenvalues, I list them by size, then this intersection, if which, sorry, I'm missing t to the minus I there, but I iterate this epsilon neighborhood of 0. I expect under the inverse map, the big eigenvalues will be the things that govern the shrinking of the intersection. So I expect the volume of this ball to be something like this. And the exponential decay rate to be given by this formula. The entropy will be the sum of the large eigenvalues. Sum of the log of absolute value of the large eigenvalues. So this is a quantity studied in number theory. This is integral of log of the absolute value of characteristic polynomial around the unit circle. This expression, where f is the characteristic polynomial of the matrix defined by the automorphism, is equal to this expression by Jensen's formula. This is a well-studied quantity in number theory, and this calculation, this way of calculating, that somehow I'm doing a local calculation inside an epsilon ball around 0, is a linearization somehow. And you can use fancier machinery to do the same kind of calculation on any of these groups. And then if you extend this a little bit, but the difficult case is the toral case, or the difficult bit is the toral bit, the collection of entropies I get from group automorphisms is the closure of the set of Mahler measures, this M of f, which is this h of t written here, for positive Mahler measures. So this is a consequence of this formula. And it's a classical problem in number theory to know whether this set of numbers, so there are countably many f's. So the f's are polynomials with integer coefficients. There are countably many of them. So this set of m of f's is some countable collection. The set of available entropies is the closure of that countable collection. Lemma's problem asks if there is a gap in the beginning of this countable collection. Is there a gap? Is 0 avoided? And this is an open problem, and for 80 years or so, and there is a smallest known example. There is a certain automorphism of a 10-dimensional torus that has less than or equal to the entropy of any other known group of automorphisms. But we don't actually have an answer to this question. If the answer is yes, there is a gap, then this quotient is countable. If the answer is no, then there is a group automorphism with every entropy. Okay. So if I can construct, the precise statement is this, and I guess formulated like this is due to Doebling. If you can construct an automorphism if you can construct for any epsilon an automorphism of a torus with entropy less than or equal to epsilon, but positive, then you can construct a group automorphism with any real number entropy. There will be one with entropy log pi and so on. So we don't know the answer to this question at all, and so we can't even say what the cardinality of this quotient space is. So that's quite a negative thing, which is where somehow what I wanted to talk about starts, that somehow you can't perturb these examples. Lemma's problem seems genuinely very difficult. So are there any situations in which you can find continua or naturally arising continua in this space G mod tilde? Somehow are group automorphisms viewed as a whole inherently discrete objects, or do they come in kind of continua families? They're called viewed through one or another dynamical prism. So here's a quite simple example. For any real number, there is a compact group automorphism whose logarithmic growth rate of periodic points is that number. So this is true. This is a kind of combinatorial version of the Lemmas problem. It's much easier, it's solved, it's easy to do.
What is that X?
So it's really important to keep in mind what the context is. The context is curly G, which is all X and all T. Right? If you fix anything here, then it's not true. For a given compact group, you can't do this by varying the automorphisms, because the compact group will have counted with many automorphisms. So you have to vary both X and T. And in answer to your question, X is some horrible zero-dimensional thing. Okay? And it's worse than that, in fact. So let me just place it in the context I want to view it. This invariant, this topological invariant, logarithmic growth rate of periodic points, if that exists, has this nice continuum, in G mod tilde. But the examples are very dishonest, they're zero-dimensional, and the maps are not ergodic. And they're just products of finite fields with some number theoretic trickery to control the growth in number of closed orbits. To ask for a more reasonable example like this on connected groups seems impossible. And the natural setting is to say I want a connected group and I want ergodic automorphisms. Probably this is Lemma's problem here. And you probably can't do it without answering Lemma's problem. So,
but the X is some compact.
this X is, for any given C, it's an explicit, sort of explicit, compact metric abelian group. It's an infinite product of finite fields. And, yeah. But if I simply added the word connected, you can't do it. You can't do this kind of construction. So we tried to see if we could get better groups, better automorphisms, that is to say connected groups and ergodic automorphisms, and get something like this example, but without stubbing our toe on the Lemma's problem. So one approach is to do more smoothing. So to ask for the number of periodic points to have an exponential growth rate is a very harsh condition to ask for. It's a very strict condition, and then I'll explain shortly why it's such a troublesome thing to try and control. If I were to average much more, then I might avoid these problems, and I'll explain what these problems are. So this is something which is sometimes called a dynamical Merton's theorem, concerns the asymptotics of this expression. So I sum over all orbits, closed orbits of length up to n, some weighted counting function, 1 over e to the h length of the orbit. And I study asymptotics of this. If I know about the growth rate in periodic points, I will know a lot about this. But this is much more smoothed. And I can have very erratic behavior in periodic point counting and still get an asymptotic here. So the project I want to describe is what can you construct, what can you exhibit by constructing compact group automorphisms for the asymptotics of this smooth quantity. And the example to have in mind is completely elementary and is not an automorphism, it doesn't really matter. Take a circle doubling map, and here is the calculation. It has 2 to the n minus 1 fixed points for the nth iterate. The topological entropy, that's the parameter h in this formula, is log 2. Because there are 2 to the n minus 1 points of period n, there are roughly 2 to the n divided by n closed orbits of length n. This is a general phenomenon. If you have exponentially many fixed points, periodic points, then most of them come from orbits of the right length. Right? Because otherwise, how would you grow exponentially fast? And a single orbit of the right length contributes n different points. So then it's just a calculus exercise that this expression, m of n, will be asymptotic to log n. So this just tells you what speed scale you should be looking for. Natural connected examples will have this thing growing like log n. And if you start playing with these connected guys, you will get log n asymptotics, and sometimes much more precise things and multiple terms and so on. And we eventually were able to construct some continua. Here I must mention that what the last 3 authors did was write down exactly what problem we had encountered in number theory, and the first author solved those problems for us. Kind of. So here are the 3 theorems, and then I'll say a little bit about how you actually prove them, what the real issues are. So the first theorem says for any real number smaller than 1, I can find an ergodic compact connected group automorphism for which this growth measure, m of n, grows like kappa log n. So this is somehow, to us, satisfying a genuine continuum in this space. And then having started, we worked hard to see what we could dig out, and you can get many growth rates. You can get any real multiple of log n to any integer power, and with considerable effort, you can get integer multiples of log n to the delta for any delta less than 1. So this means in this strange setup in which you are varying both the automorphism and the groups, you can exhibit in a quite controlled way this huge diversity of orbit growth behavior. Very strong sense. So what is going on here? Why is this? What are the issues here? So the first thing to say is that you have to you encounter very difficult problems. So let's say I'm going to make a construction here. What does that mean? It means you choose a set of times S, okay, which will define some specific subgroup of Q here. Then so that defines some group in Q. Then the dual group is some compact thing with an automorphism. Let's say this doesn't really matter. It might as well be dual to double. Could be anything. That's not where the problems lie. Then you use some machinery to compute X a formula for the periodic points. So let me just go through this very quickly. If your set S was empty, that is to say, if in this picture you didn't invert any primes at all, then the group you'd construct would be Z, which is dual to the circle, and the map would be circle domain, which would have 2 to the n minus 1 points of period n. But as you invert primes, more and more primes, you kill some of the closed orbits and you reduce the number of periodic points. And explicitly, the formula is, I'll explain where this comes from, the formula is this. So what that means, heuristically, is you take 2 to the n minus 1, you factorize it, and you delete all the primes that were in S. So now what is the question you're asking? If you were trying to just measure the growth rate in periodic points, what could you do? You're in big trouble because every now and then, probably 2 to the n minus 1 is prime. Right? Almost certainly. When that happens, if you have included that prime, this quantity is 1. And if you haven't, this quantity is as big as 2 to the n. So if your aspiration is to make this thing grow like 1.3 to the n, you can't. That's why you need to do this smooth. So you have to avoid these problems from classical number theory problems. And then you smooth this thing. So somehow the chain of argument says, here is a formula for fixed points. I can deduce from that a formula for the closed orbits. Then I do this weighted average of closed orbits. Try and extract dominant terms. Try and construct a set of primes to make this happen. Somehow. So the whole game becomes constructing sets of primes, and this is what I mean by constructions in one solid. You're constructing these things in one-dimensional solid. Incidentally, the reason you work in Q is partly that it was enough to construct the examples we were after, but also it's almost the only group of any interest for which you can write down all the subgroups. You can just write down the subgroups of Q. It's a very classical exercise in group theory. You cannot write down the subgroups of Q squared, for example. That would be a completely different kind of enterprise, and I don't know what happens there. But anyway, we work in Q, we construct sets of primes, and we work primarily with these subrings. Set of primes, fix a map on a subgroup of things whose denominators are only divisible by those primes.
Yeah, that is theorem that you cannot write down the subgroups of Q.
Yeah. This is, I don't understand what, I can say the words in the statement of the theorem, but I don't know what it means. The equivalence relation is not treeable, the set theorist tells. This is the result of calculus, that you cannot somehow describe the subgroups of Q squared. I don't really know precisely what is meant by that. So then I have to do things to construct sets of primes, and I just want to describe an example of the kind of statement you need. So this is a typical question in the construction. Start with some real number delta, and find a set of primes with the property that the sum of log p over p as I run through those primes up to n is asymptotic to delta log n. This is not too bad. If delta is rational, this is easy to do. If delta is irrational, you need to work a little bit. You need to understand a bit about where primes appear. And throughout, you need to control errors, because once you reassemble all the machinery into this smooth thing, the errors try to accumulate and hurt you. But you need to do this simultaneously with some other things. So you need to do this, and at the same time have the ability to construct a further subset with a controlled size of Euler product, or Euler-like product, and controlling this sum because this contributes to one of the errors, and so on. So it's a very, you can, I hope, get some sense this is kind of a happy stamping ground for analytic number theorists of the right sort. Certainly not for me. But you can do all this stuff. We know a lot about the primes, and we know about gaps between primes. We know lots of things. You can use all this machinery to construct these things. So, in some sense, this answered my original question in this very narrow, specific sense that this mysterious space of all compact group automorphisms has very naturally occurring continua, measuring growth in units. And just to finish, I want to say a little bit about the sort of general situation, which is I fix a group that will act by automorphisms on various compact groups in various ways and ask the same question. And here, of course, as many of you know, completely different phenomena appear. So I'll just mention a few examples. So for ZD actions, if D is bigger than or equal to 2, it's a completely different world than if D equals 1. So everything I've said so far is Z actions. For Z2 actions, there is a phenomena where measurable isomorphism between two such systems under some hypothesis is forced to be an affine map. So this is a completely, this is almost the opposite to what happens in for Z actions. And a very beautiful observation of Siddhartha, back of the room, is that the hypotheses really matter, and without the hypotheses, the statement is not true. There are mixing actions of ZD of this algebraic sort that do not have this measurable rigidity, because they're not irreducible, but they still have another kind of rigidity. There's a long, complicated story that starts there. Topological rigidity survives, and this is a theorem that's a real mouthful because there are many hypotheses, but the thrust of it is that the topological rigidity, that is to say this beautiful result of Adler and Paley, that homeomorphism conjugating two ergodic automorphisms is actually an affine map. This survives into ZD actions if they have entropy, if the target, if one of the systems has finite entropy. The system you are conjugating to has finite topological entropy, and if not, it's not true. If the entropy is infinite, then you can easily construct exotic topological conjugacies. And you can see this already. This is completely independent of D. This is a different kind of phenomenon. You can see this already. If I take the circle as alphabet and a full shift, and ask what topological conjugacies exist between that and itself, well, you can start with any homeomorphism of the circle to itself. Make a shift commuting, and you've written down a topological conjugacy. It's certainly not affine. And that's possible because the entropy is infinite. So I want to end here because I should, but also this is somehow the beginning of such a long story I can't ignore. Thank you.